Okay, so we'll take one example and do Prim's problem first. The problem. Okay. This we saw what spanning tree is, right? And there will be a cost for each one of them. We need to find the minimum cost. Okay. Let's look at the formal definition. What is in your textbook for a spanning tree? Okay. Okay. The input, you will have a weighted graph, right? Because you want minimum, obviously there should be some cost to it. So that is why you have a weighted graph. Okay. So how do you represent weighted graph? It's a graph with vertex and edges. V and E means vertex and edges, vertices and edges. Okay. So W is the weight of a subgraph. Okay. And what is W? It is the sum of weight of all the edges in that subgraph. So we last class we went about the definition of a subgraph, right? Subgraph is a part of the original graph. Like my graph is something like this. I need to find a subgraph because spanning tree is a subgraph, right? So every subgraph, and while I'm building that, we saw, right? We will build slowly, we will start building like this. And finally, you will come across like this, right? So slowly you're building. This is your subgraph 1. This is your subgraph 2. And finally, this is your subgraph 3. Right? So every subgraph will have a weight because you'll have a weight for this. Say 10, 15, 5, right? So every subgraph will have a weight. So that's what this definition is saying. Okay. In a weighted graph G, which contains vertices and edges, the weight W of a subgraph is the sum of all the weights. Sum of the weights of the edges in that subgraph. Okay. So this is the definition of what a graph is, what a subgraph is. Now, what is a minimal spanning tree? A minimal spanning tree, right, is a spanning tree with minimum weight. Right? So minimum spanning tree is a subgraph which connects all vertices and whose weight is also minimum. Okay. Now let's take a look at the Prim's algorithm. So while you start the Prim's algorithm in your, say if it comes in your question paper also, right, they will give you this graph. Right? And you need to first identify this is a weighted graph and this is an undirected graph. Right? So I can solve this. I can find the MST in 2 ways, Prims or Kruskals. If in the question they have explicitly told Prims, you need to follow a particular algorithm. If they have told just find minimal spanning tree, right, you can use either Prims or Kruskals. Okay. So first step is you need to build the adjacency matrix from this graph. This will not be given in your question. Okay. This will not be there. This you have to write down. You have to find how many vertices are there. 1, 2, 3, 4, 5. So I build a 5 cross 5 matrix. So I have 5 vertex here. I have 5 vertex listed here. Right? And because this is a weighted graph, I have given weights for each one of them. Okay. So this is your second step, building the adjacency matrix. Because we have already spent time on how to build, I will not go in detail. Okay. I will start directly with the steps of Prim's algorithm. So Prim's algorithm basically has the concept of visited vertex and unvisited vertex. Visited vertex means something that you have already checked and you have drawn a graph. Like for example, here, these are all unvisited vertex because I have not yet visited any, right? So I put all of them in my unvisited vertex. Okay. The moment you have this edge drawn, right, you have already finished vertex 1, right? So I put in the visited, I've already visited 1. Now I need to continue from the rest of the vertices. Okay. So you need to build a list of visited and unvisited vertex. Okay. So first it's a step 1. You don't have any visited vertex. All vertices you will put it in unvisited and your initial graph will be like this. Okay. You just have to put your vertex. Step number 2. what you need to do is pick any vertex. Say, let's pick the first vertex. Okay. Now you need to find out from 1, what are all the possible edges available for me. So how do you get that? You need to make use of your adjacency matrix. So this I have just copied everywhere so that I have a reference. So when you're doing this in your notebook, right, you can also start in a fresh page and keep this handy, because every step you need to look at this adjacency matrix. Right? So when you look at adjacency matrix, you're looking at vertex number 1. Okay. My screen is shared, right? Yeah. Yeah. So I'm looking at vertex 1. So I need to look at this row, right? And I need to see what are all vertices 1 is connected to. So wherever you have number, you know that 1 is connected, right? So you know 1 is connected to 2. If you look at the original problem, right? By looking at this here, you know that 1 is connected to 2. 1 is connected to 3. 1 is connected to 4. And 1 is connected to 5 also, right? So you get that representation here, okay?
Yes, ma'am.
So now we know that there are 4 eligible edges, right? Our problem is what? We need to find the minimum, right? So which one you will pick? Will you pick 1 to 2, 1 to 3, 1 to 4, or 1 to 5? Which edge will you pick? You got the question, what I'm asking? I'm inspecting first vertex, vertex number 1. I have possibly 4 edges coming out of it. So what does this mean? Vertex 1 is going to 2 with cost 11, is going to 3 with cost 9, is going to 4 with cost 7, it's going to 5 with cost 8. Which cost is minimum in this?
7, ma'am.
7, correct, right? So this is how you're used to seeing the graph. Now you should make the same interpretation by looking at this matrix also. So when you look at this, it takes some time, maybe 1 or 2 times you draw this matrix, you can get the diagram out of this, right? Because virtually diagrammatically it's easy for you to understand. So you should learn how to get it from this table also, right? If you don't understand this, like it is getting hard for you, you do this. What this means, it means 1 is connected to 2, 3, 4, 5, right? And you draw your weights here. So that way it is easy for you to visualize also, whichever works for you, right? So now you know the 7 is the least cost and the connection is between 1 to 4. That is what we will pick. We will pick the minimum cost vertex, right? So how do you represent this? You have already visited, in your second step, you have visited 1, okay? And these are the possible edges from 1 to unvisited vertex, right? So from 1 to 2, you have 1 to 3, you have 1 to 4, you have 1 to 5 also, right? This is how you represent the edge. 1 comma 2 means you have an edge from 1 to 2. Similarly, the rest of them. And here you're putting all the cost, right? 1 to 2 took 11. Same thing, what you read from here, I'm just putting it here. So you have 11, 9, 7, and 8. And the minimum is 7, which actually corresponds to this edge, 1 to 4 edge. Right? Once you have made this looking at the table, all you have to do is just draw that. Yeah. So just draw 1 to 4 line. This is something that you have selected. Right? So in your next step, you pick from there on. You visited 1. So next you have to pick this 4th vertex. So that is what you will put here. In the visited vertex, you will now also add 4. In your unvisited vertex, you will put the remaining one. Right? Now here you need to see, do you have anything from 4 to 2, 4 to 3, 4 to 5? That is what you are going to check now. Right? Now you are going to check this 4th one. Right? So here you need to check only this one, 4 to 2, 4 to 3, 4 to 5, right? This is important. You will not check everything. You will not check 4 to 1, 4 to 4 also. You will only check what is unvisited. That is very important. This is there, no? Only this you have to pick, right? And you also, basically what you have to do is you have to pick from visitor to unvisited, right? So this is one combination. You can also check now from 1 to 2, 1 to 3, 1 to 4, 5 also. This also you need to check. So basically you will check both these rows, 2, 3, and 5. This marking is important. You're not checking everything. So I'm checking visited. Visited is 1 to 4. Okay. So from here, I will not pick 1. I will not pick 4. The rest of them, right? I need to pick. So the one that I have picked, I have highlighted here. Now in this, which one is the minimum? So you have 11, 9, 8, 4, 12, 6. Which one is minimum? So basically what we are doing is after this step, after building 1 to 4, right? I can start growing the graph like this also. Like I can pick which from 4 I want to connect or from 1 I want to connect, right? Both possibilities are there. That is why we are checking all the combinations of both 1 and 4. That's what I have highlighted here. 1 and 4, all the possible combinations for me, right? In this, I have to pick the least one. So least one here is 6, right? When I compare these numbers, least one is 6. What is 6? Which edge is 6? Can anybody tell?
4 to 5, ma'am.
Yes, 4 to 5. So that is why I'm picking this edge, 4 to 5. Although there are for me other possible edges, like I have from 1 also I have an edge. I'm not picking that up because that is costly, right? So I pick this 4 to 5. Okay, now after this, in your next step, let's do that next step. In your next step, which one will be visited? What you will put in visited vertex? We'll do this once more, okay, just for you to understand. I know this is first time you're seeing this, it may be a little confusing, but just let's do step by step, okay? So in your next step, which one will be visited? And which one is unvisited? You visited 1, you visited 4. So after this, after drawing this, you have also visited 5, right? So your visited is 1. So basically whatever you have drawn the graph, that is your visited. You have drawn graph between 1, 4 and 5. Your unvisited is only 2 and 3. Right? So now you need to find a combination of from visited to all unvisited. Right? So how do you do that in the graph? You have to first highlight all your visited. So your visited is 1, 4, and 5. Right? And which one is your unvisited? Only 2
and 3.
And 3. Correct. So I will pick only these numbers. I'm not picking others. Right? I'm only picking this. Right? So once you highlight in your matrix, it is very easy. In this, which one is the minimum? 9, right? 9 is minimum. When I say 9, which edge is that? It is between 1 to 3. Correct. So that's why now I build the graph as 1 to 3. I added this new one. Okay. Now after this step, your visited will become all of this, wherever you have drawn the graph, right? So 1, 2 is not yet visited. 1,
3, 4,
and 5. Right. And your unvisited is
2.
Exactly. So now when you highlight, you need to be careful. You need to check all the visited So that's why, like, if you're doing this, no, have some color pencils with you. It helps a lot, right? So you have to check all the visited to only unvisited, which is 2 here. So you are basically looking at only this one, right? So in this, the minimum is 11.
11.
11 means 1 to 2. So I draw this 1 to 2 graph. Okay. So after this step, visited is 1, 2, 3, 4, 5. Anything unvisited?
Nothing.
Nothing. So at this point, we stop. So now you have actually built the spanning tree. This is the spanning tree. Okay. So what is the cost? You just have to add up all this cost. So 11 plus 9 plus 7 plus 6. Right? You get 33. So you got your minimum spanning tree and you got the cost of that also. Okay. So I will stop at this point. Next class, we can take a look at prims or Kruskals also. And we can just do one sample. We'll take one sample graph and run through this. Before ending, no, I'll just, now we have seen how it is done, right? I'll just, we'll just look at this. How do you represent this in an algorithm format? Same thing, what we did, okay? So how you will do this? What is your input? Input is a graph G, right? It is connected, undirected, weighted. We know this, right? So you need to build the cost adjacency matrix, right? And you know that number of vertices are n, okay? Your output is a minimum spanning tree called T, okay? Now what you will do for every, before you start the algorithm, right? You need to mark all the, you need to maintain a list of visited and unvisited, right? And initially, you know, visited is all empty, right? So what you do is you just iterate the graph, okay? And you mark all the visited as 0. Basically, you're maintaining a visited list, an array of visited list, okay? And all you're marking as 0. So the moment you visit that vertex, you will change this to 1, okay? So initialization, this is only initialization. Here it is there, no? Your actual algorithm starts here, right? You will pick, by default, you can pick the first vertex. When you say u equals 1, that means you're picking the first vertex. And in that visited graph, you put this as 1. Because I'm picking the first vertex, I know that it is visited. Now there is a while loop, right? Because now you need to go check everything, right? Till when will you repeat this? Till your unchosen vertex, or you can say unvisited vertex. This is more easier to remember. Unvisited vertex. Till there is still some vertex left in this unvisited, we have to keep doing this. Once your unvisited becomes empty, you need to stop it, right? What you need to do every time, you have to pick the lightest edge. Lightest edge between what to what? Between any chosen u to any chosen v. U is nothing but unvisited, and v means visited. Right? That's what we did. We picked all the possible edges from visited to unvisited, and we picked the minimum. See, once you understand the algorithm, you can rewrite this in your own sentence also, right? Basically, what we are doing is we are picking one edge, right? U to V. What is this U to V? It's the edge, which is the lightest, which is the minimum cost between unvisited to visited, right? And then that vertex, we are marking it as 1. We are marking it as visited. And your overall cost, this we did it in greedy algorithm, it is always like this, right? You will find the cost at one step. You found this cost, you're adding it to the total cost always. You're doing a union, right? Because as you build this, you got this, right? You're adding this to the total cost. Next step, you will find something else. You're adding that to the total cost of this previous problem. So it's always the union of your previous computed cost with the new edge that you're building it. Okay. Okay, let's stop here.